Newton's first law, the law of inertia, states that objects at rest tend to stay at rest unless an external net force acts on the object. So with this experiment, we took this rod here, placed it near this rod, and then withdrew whatever force we had on it to move it there, so we had no more external force on it, and then it started moving anyway. It accelerated towards a stationary rod, so there must be a force present. We don't see the force, it's not a contact force, but we now call it the electrical force. And as with all forces, we measure it in newtons. A little bit more of history. In the late 18th century, several physicists, Priestley and Robeson, reasoned, and Robeson measured, which is very important, that the force between two objects followed the same principle as the gravitational force, and the force between two charged objects depends on the inverse square of the distance between them. Charles Coulomb published a paper in 1785 based on some more detailed experiments that definitively proved the previous slide, and that the force was also proportional to the size of the charges. He used a torsion balance for his work, and that was based on the same principle as Henry Cavendish's experiment that measured the gravitational constant. Here's Coulomb's law. The magnitude of the electric force is equal to K, which is Coulomb's constant, times the magnitude of charge 1 times the magnitude of charge 2, divided by the distance between them squared. 1, 2 does not mean 12 there, it just means the distance between charges 1 and 2. So here's the Coulomb constant, 9 times 10 to the 9th Newton meters squared per Coulomb squared. Here's Q1 and Q2, the absolute value, and R12. If we have point charges, the distance is just between the charges. But if you have spherical objects, the distance is between the centers of the objects. Please note the striking mathematical similarity to Newton's law of gravitation. So instead of K, you would have G, the gravitational constant, and instead of the charges, you'd have M1 and M2. You don't need the absolute value because masses are positive, and you divide it by the distance between them squared. Coulomb's law is used to calculate the magnitude of the force. Each object exerts the same magnitude of force on the other, but in opposite directions. And of course, Newton's third law applies to all forces, not just mechanical contact ones. The direction of the force is found by looking at the signs of the charges. Like charges will repel each other, and opposite charges will attract. Comparing the two forces, the electrical force and gravitational, neither which are contact forces, right? They don't have to actually physically touch you. Both forces are expressed using similar math, where the magnitude of the force decreases as 1 over r squared. Now, electrical force can be attractive or repulsive. Like charges repel, opposite charges attract. Gravitational force is always attractive, until the physicists out there truly prove dark matter exists, and then you might have something different, but at the moment we say it's always attractive. The electrical force is 10 to the 36 times stronger than the gravitational force.